All right, for record, all students are here. Okay, for chapter 3, these are the chapter that we need to focus on. Laminar turbulent flow, entrance region, fully developed flow, transition, major loss, Moody chart, Darcy-Weisbach equation, and Cheji equation. Let me know if you're not able to hear me or you're not able to see anything on your screen. All right. Now, at this stage, you should able to tell, based on Reynolds number, you should able to tell if the flow is laminar or turbulent, and what happened when the flow is at the entrance, and then how it changed to fully developed flow in a pipe. All right, and then in my slides, I already covered the derivation for this Darcy equation and Chezy equation. All right, so please have a look into my slides on their derivation. All right, again, important is the application of these two, how we use it. So today we're going to look at this component, major loss and Moody chart, mainly on a Moody chart, how we apply it. So for the first hours of today, we're going to conclude, we're going to cover chapter 3 for this morning. All right, and just for your info, chapter 3 is inside your midterm test content. Okay, just look at your tutorial sheet, the diagram above question 32. You will see this table 8.1, right? Table 8.1, it gives you some information about the roughness, surface roughness inside the pipe. So different material will give you different quantity of the roughness. And in the exam later on, be careful, you're looking at the second column that I'll show you now, which is the unit SI, and millimeters, mm's. So be careful on the unit, and you have to be very alert to the statement or question given. So there are different types of material, right? Yeah. And this is the Moody chart that I showed you before we end our class last Friday. This is just above question 36, page 13. So above this one, this chart is very useful to help us to find whether the flow is turbulent or not turbulent. And we have three axes again, three axes for this chart. We have a friction factor, F, on the left-hand side. And then right-hand side, we have the surface roughness divided by D. So be careful on the unit that you use. In the chart that I just show you just now is in mm. So be careful when you do division. So it's surface roughness divided by diameter. So in the table is mm. So when you divide, make sure you use same unit also. All right, because this is just a ratio. On the right hand side axis, this one is just a ratio between surface roughness and the diameter of the diameter. This one referring to the diameter that the water contact with. It means if inside a pipe system, you know that pipe system is a fully filled condition. So it means that the diameter we are using is DI, which is the internal diameter of the pipe. So be careful on the D that you choose. All right, so this is just some highlight for the axis. And then on the bottom there, we have a Reynolds number. Reynolds number will give you the rho Vd divided by mu. This is the viscosity. So if you are already take the introduction to thermofluid, or you have the textbook, All these parameter you can find in table 1.8. Reference table 1.8. Okay. Now in here you will see inside the content you will see what is laminar flow. Where is laminar flow? Which is by definition is 2100, which is around here, right? 2100. So you can see the scale here. So this is 1000, 2000. So by definition is 2100. So it's about here, all right? It's about here. So here is 2100. Less than 2100, then you'll have laminar flow. Okay, 2100 here. And then by definition, if your Reynolds number more than 4000 here, 4000, if you follow this line, so it has been drawn like one line for you already. So all the value that more than this line, this vertical line, will be turbulent flow. Right, will be turbulent flow. Okay, then there we have a transition range. So in transition range, here we don't have a line here because it's a very complex process, and it's very hard to measure. Very hard to measure the velocity and the density and all this. So that's why we don't have data inside the Moody chart. And the Moody chart is published, I think, more than 20 or 30 years. So it's a very old chart, but it's still valid to use for normal life application. Okay, just let you know that there's a chart called Moody chart. And it's very useful to find either the friction, roughness that you use. When this chart is very useful when you want to do some design work for your for the system that you design that deal with the hydraulic. Okay, just a notes on the chart, right? So for laminar, your friction is for 64 Reynolds number. Right. Your friction factor here, this region, the friction is 64 Reynolds number. And for turbulent flow, yeah, so just let you know when you have a large turbulent flow, is independence of Reynolds number, meaning is you can say in this region, right, is wholly turbulent. So it doesn't matter what value of your Reynolds number, it will be turbulent flow. Okay, so this is another diagram with above your question 36 on the tutorial paper. So this is just a further definition, a further detail on the Moody chart, right? So this one you can go and study, and it will help you to in your exam also, right? So yeah, but basically all the main component already covered. Yeah, if you see the bottom axis, you'll see the v hat. V hat means average velocity, and v hat average velocity always useful when we have a turbulent flow, right? And if you forget what is v hat, you need to go back to the slides for revision, how to find v hat. Okay, so you need to fill in this answer, which is this one is an additional equation. When we look at Moody chart, it's called Colebrook equation. So 1 over square root of friction factor equal to -2 log times the surface roughness divided by d, which is on the right hand side axis, divided by 3.7 plus 2.51 divided by Reynolds number times the friction factor again. And this Colebrook equation is valid for all the non-laminar range in Moody chart. It means after this straight line, this Colebrook equation is valid for on the right hand side of this vertical line. Because by definition, turbulent flow, we have turbulent flow when our Reynolds number is more than 4,000. Another one, another one is called Helen. Helen equation. So Helen equation is the answer for question 37. It asks you to fill in the equation of Helen equation. So Helen equation given by 1 divided by square root of the friction factor equal to negative 1.8 log times the surface roughness divided by diameter divided by 3.7 power 1.1 plus 6.9 divided by Reynolds number. So if you look at these two structure, if you compare between Colebrook equation and Highland equation, if you look at the right hand side component, the friction factor is a bit different between these two. And the constant value that they use also different, right? But both of them are valid, valid to use. Because both of them are researcher that do research in the part flow, right? So both of these are found by using experiment data, so it's valid to use. Okay, so we have done question 37, and then we go for question 38, which is very important for your coming assessment. So we look at question 38. So question 38 gives us that the air under standard condition. Standard condition means 15 degrees C and standard pressure. Flow through 4 mm diameter. And average velocity here is 15 meter per second. Again, typo error. This is meter per second. For such a condition, the wood would normally be turbulent. However, if precautions are taken to eliminate the disturbance to the flow, means we use a smooth tube, the air is dust-free, and tube do not vibrate. So it may be possible to maintain the laminar flow. So there are two tasks to ask us to determine. First, determine the pressure drop, which means our delta P in a 0.1 meter section of the tube if the flow is laminar. So the first case is look at laminar case. The second one is we need to see if what happens if the flow is turbulent. All right, mean we still need to see the pressure drop, but the second case is turbulent. Right? So we are now at question 38. All right, let me check the attendance of you here. All right, now I think there's enough space for you under the question 38, so you can straight away write the answer below there. Right. Yeah, just as a note, side note, if you see the standard condition, it means that your density, the density of air is 1.23 kilogram per meter cube, and the viscosity is
This is
1.79.
the standard calculation, sir.
This is a
I mean standard value.
uh, this is the standard value when your air is under standard condition.
Okay.
Means that at 15 degrees C, right? And because when you want to compare your data with all the scientists around the world, so we need to have a reference benchmarking. So it means that everyone's speaking at the same level. Means that we conduct all our experiment at that particular or refer to that particular temperature and pressure, so that the data we can compare, right? So yeah, so this standard condition also this word this term standard condition also is very sensitive. So be careful when you write your report in your FYP, in your final year projects report, or in a normal report also, lab report also. So uh, if you're not if you're doing comparison, then and if you're using standard condition, this word mean you're referring to a table, a standard table, or there's a property table that you refer to. All right. So density, this one standard already. Right. When right these two value we use when we have the standard condition statement. So 1.23 and 1.79. 10 power negative 5, the unit is Newton second divided by meter square. Okay. So again, the equation that we're going to use is Reynolds number. Reynolds number equal to rho Vd divided by the viscosity. So even in the exam you forget, you will see Moody diagram. So this equation is under below the horizontal axis of the Moody chart. So it's exactly the same. Reynolds number equal to rho Vd divided by mu. Okay. And yeah, so if you substitute the standard value for air under standard condition, you have rho already. Velocity is given, again a typo error. So this the average velocity is 50 meter per second. The stroke is missing. So just take note on the question there. V is given. D is given. Diameter, again, be careful on the unit. Don't straight away use 4 mm. You need to change it to meter, because all the unit inside the all right, all the value inside the equation here is in meter. Divided by mu, also in Newton second per meter square, so also in meter. So if you do the calculation, all right, substitute all the value. Okay. You do the calculation, I will check attendance. Joshua, are you there? What is the value for the Reynolds number?
Sir, I can't see the question.
The question is on the tutorial paper. I asked you to download and print out, right? Is tutorial question 3.8. And I already mentioned how to find the Reynolds number just now. It's under a certain chart. The chart is called Moody chart. Jia Wing-Fong, you are the second person I'm going to ask. Stand by for the number of Reynolds number. If Joshua not able to answer. So I'm going to give you another 30 seconds to find. So Joshua, what is your answer?
Sorry, sir, I got lost. I don't know.
Can you show me can you open your webcam and show me the tutorial handouts? Will you print out?
Sir, actually, for the tutorial, I'm just using the soft copy, actually. Haven't printed out.
Okay. Share screen. Share your computer screen. I want to see your tutorial paper now.
One sec, sir.
Chia, you already found the answer already?
So is it 2000 times to the power of 3?
2000. Your answer is 2000.
Not sure, sir.
You not sure? Tell ready your equation. I was going to ask you how you get the 2000 answer later. Joshua, please share your screen. Right, this whole session will be recorded, just for your info. Joshua, please share your screen.
Sir, can you see my screen?
Nope.
I actually have to press the open share tray, right?
You go at the you go to the below the themes. You see there's a row of icon that you can click. There's a monitor there beside the mic. There's a share option there. So below your screen, there's a row of icon. Then there is a monitor screen that with the arrow pointing up. Click the share content and then go to the desktop. Click content. You will see the screen on the left hand side. Desktop. Click that desktop and you're able to share.
Can you see that?
Yeah, everyone can see already. Okay, now what is the equation for Reynolds number, Joshua?
It's P V Y nil.
What is the equation? What is the formula for Reynolds number?
Yes, sir. It's rho VD over nil.
Okay. All right. So you have Reynolds number, and then you go to question 38. Yeah. So just now I give you the standard value for air, right? What's the density for air? All right. Yep, Joshua, you can close your screen already. Okay. Just now I asked Jia, right? Jia Wing Fung, right? Okay, Chia.
Yes, sir.
Yeah, Chia, just now the Reynolds number, what you get? What's the value? What is the value for Reynolds number? Chia, how you get Reynolds number? Can you share with us how you get Reynolds number?
So I have the raw video of a meal, right? We have the raw is now we have the standard condition. The
Mm-hmm.
raw is 1.23, right?
Okay.
Kg per meter. And times the V is 50 meter per second.
Mm-hmm.
Then the diameter would be 4 mm means we have to convert it to meter.
Correct.
So we divide by 1000 times 1.23 times the V, then divided by the mu, which is 1.79 times 10 to the power of -5.
So what is the answer?
It's so I need to get my conversion right first. I think I've done something wrong. It's 13,000. It's 137,430.
Okay, so you get 137 something lah. All right. Now,
Yes.
what does this number tell you? Is this a laminar or turbulent? Chia?
It's a turbulence.
Turbulent, Okay, good, excellent, good. All right, now from this number, we know that it's turbulent flow. So if your number is less than 2100, 2100, then it's laminar. So when you want to solve chapter 3 question, always start with the Reynolds number so that you know whether you want to use the laminar flow equation or what is the state of the flow. So it's very important. All right. Now we start to solve question already. Because from the Reynolds number, we know that the flow is turbulent flow. However, section A, it asks us to assume that the flow is laminar. So we need to use the Darcy friction factor, which is in my previous slides. Right. So this factor is for laminar flow, given by 64 divided by RE. It is also I mentioned in the when I explained about the Moody chart. Okay, write this statement in under the question 38. So Darcy friction factor is only applied for laminar fully developed round pipe flow only. This Darcy friction factor is given by F, which is the friction factor, equal to 64 divided by Reynolds number, meaning that the friction factor that we use for laminar, we use this equation. Later on, we will import this friction factor into our Moody chart, because on the left hand side of the Moody chart is friction factor. This is how we find the value. Okay, now just now our Reynolds number is 137 something, right? So I just simplify it to 13700. So I take this number, all right? So 64 divided by 13700, I get my Darcy factor, Darcy friction factor. And again, this equation 64 divided by Reynolds number is only applied for laminar fully developed round shape of pipe. Okay, so be careful on when you want to use the equation, right? So we have friction factor equal to 64 divided by Reynolds number. So you use your calculator, 64 divided by 13700. You'll get around this number 0.00467, right? And if you refer to the Reynolds Moody chart on the left hand side, you know that your friction factor is only 2 decimal place. So uh, it is fine that if in your answer you have like 4 decimal place or 3 decimal place, it will help you to plot a better chart later on. Means you if you have a more decimal place, then you know where to put your pen on the graph. Okay, and we call the change of pressure equation delta P equal to F. This is our Deci equation also. Delta P equal to F L divided by D times half rho V square, right? Delta P equal to F L divided by D half rho V square. You substitute all the value because your rho is given, V is given, D is given, L in this question is given because it's given 0.1 m section, which means it measures from the reference point up to a 0.1 meter section. Friction factor you define, which is 0.00467. You substitute the value. Again, all the units we use here is unit SI. After you do conversion, you will get in kilopascal or meter Newton over meter square. Okay. So we have solved for the first one. This is by calculation. All right. So section A is application of Darcy friction factor equation. F equal to 64 divided by Reynolds number. And then we pull out the equation. Delta P equal to F divided FL divided by D times half rho V square. Okay. And another alternate equation will be used at the bottom there. You will see on the screen, you will see another formula that you can use is delta P equal to 32 mu LV divided by D square. So derivation of these two equations was covered in my previous slide. So make sure you go and read it. All right, you substitute all the value, you will still get the same value, which is 0.179 kilopascal, or if you take out the kilo, you'll get 179 Newton over meter square, which is equivalent to Pascal. So in exam, if the exam doesn't state either in Pascal or in Newton meter square, both answer also correct. If the exam doesn't state which unit to put, right? You can give in Pascal or in Newton over meter square. But normally the unit will be stated clearly in the exam question statement. Okay. So again, we are using unit SI. So if your answer is in imperial unit or English unit, then you have the wrong answer, right? Because unit SI and imperial will be the different, right? Okay. Now for part B, where we look at when the flow is turbulent, so how we process this case. So again, this is just a dimensional analysis equation. So also covered in my slides. Make sure you go and read it. It means that what does this mathematics equation means is that when the flow is turbulent, the friction equation, the friction factor only influenced by these two parameters, which is only influenced by Reynolds number and also the right hand side axis of the Moody chart, which is surface roughness divided by D ratio. Right. So from table 1.8 just now, which is in the above question 32 in your tutorial. Right. In this one, the material here is 4 mm diameter drawn tubing. So if you refer to table 1.8, we are using drawing tubing here, right? Or you can refer to your tutorial which is above question 32. So be careful, we are using unit SI, so we are using 0.0015 value for surface roughness or equivalent roughness later on. So don't use the wrong value. Yeah. So we do the calculation. We take surface equivalent roughness divided by diameter, and again this one is internal diameter. Then we will get 0.00375. Our Reynolds number just now is 13700, or you convert to index format, because our Moody chart is in this format. So it will be helpful for you to draw the correct position of reference line later on. Right. This is just a safeguard when you use the Moody chart, right? So because sometimes this whole number will confuse you a bit. So let's look at how we use all these number and how we apply the Moody chart, right? Okay, now your value for on the right hand side, the equivalent divided by D, just now we get 0.000375. Reynolds number is 1.37 times 10 power 4. So how we enter the Moody chart? We enter with Reynolds number first, which is at the bottom of the chart there, because our component is 1 point something 10 power 4. So you look after the 10 power 4 between 1 and 2, because this mark is 2.10 power 4. This is 110 power 4. So our value is between these two, and then you do your calculation. This is 1.5. Yeah, because you divide it by 3, so each one of these is about 0.3, 0.3. So 0.3 and 0.6 each line, right? Check. Okay, this line should be a bit to the left, right? But you start with the Reynolds number, and then you enter from the right with 0.04, because our value is 0.00375. You round it to the closest, so we have 0.004. So, and then you follow this line follow this line from the right, follow this line from the right until the intersection point of this line, and then move to the left. You get your friction factor, right? So you get around 2.8 something, 2.08, right? So the arrow here is not showing the correct position because the line that I showed just now. All right, it should be a bit to the left. So your value will get around 0.028. Okay. So again, the line that I show on the screen here is a bit off from the actual position. I just show you the steps. So first one, you start with the Reynolds number, you draw a line, and then you can either enter from the left or right. In this case, we have the right value, the right hand side value, 0.00375. We enter from the right, intersect with the vertical line, then draw to the left. You get one value on the left. In this case, we get around 0.28, 0.028. Okay. Again, the line that I draw on the screen here is a little bit off. It should be a little bit more to the left. All right. Because when you put the line in the PowerPoint slide, it will off a bit. You cannot go to the exact location. So important here is that you know how to enter the Moody chart. Sometimes you get from the left, sometimes you get from the right. But again, Moody chart, we have three axes. So normally question in final exam or exam, you have either two of these. You either have friction or you already have a Reynolds number, then you enter, then you move to the left or right to get the missing value. Sometimes you're given Reynolds number, given the friction, and then it asks you to modify the pipe. It asks you the diameter of the pipe so that it meet the condition, that the specific condition that needed for operation. Okay, so I think this step is not very complex. All right, so it's very straightforward. Only mistake here is that some of you might enter into a wrong line, and then you confuse. All right. Okay, so we move forward. So from the Moody chart, we get our friction factor equal to 0.028. And then pull our equation, delta P equal to friction factor times length divided by D times half rho V square. You substitute all the value, you'll get 1.079 kilopascal. This is from Moody chart, right, by using the Moody chart. Another one is that you can use Helen equation, but it's a little bit complex. So I would recommend you just use a Moody diagram. Okay. There's an alternative way to find the friction factor. Right, a bit lengthy. You still get the around 0.028, right, around this number. All right, so if you use calculator and punch in the value for Helen equation, 1 divided by square root of friction factor equal to something. So if you press all the value in, you will get 0.0289. Okay, this Helen equation is for question 37, right? It's an application for question 38 also. So there are two.
Yes.
Yes.
At the I mean the friction vector, the equation.
This one,
They have
right,
the
Helen, right?
no, the first one.
This one.
Above that.
This one. I mean this one. Is it this one?
Yeah.
Okay.
The beside the Reynolds number is what the
Oh,
unit?
it's a pi.
Okay.
Pi. So it's just this presentation is just a mathematic presentation. It's just saying that when it's a turbulent flow, your friction factor will be affected by these two parameter. It's just that it's just a mathematics symbol saying that this parameter f is influenced by these two, influenced by
Oh,
Reynolds number and the ratio of your surface roughness divided by d. Means you change Reynolds number, friction factor will change. You change this one also affected. It's just a mathematics presentation. In this symbol you'll see when you study the dimensionless analysis.
okay, sir.
Yeah. Someone saying something, right? Any question? Okay. Any question for question 38? Any question? No. Okay. Okay, so this one, let's see, this one is I think this slide is not inside the tutorial question. All right, so I go very fast for this one, so later you can come back. I think the slide that you see on the screen here is not inside the tutorial handouts. All right, it's just another example how we use the Moody chart and all the equation, right? So yeah, so for the next like 3 minutes, after we cover this one, we go for a short break. Right? So yeah, pay attention on the screen. All right, so this is again this question is not in the tutorial question. It's not inside. It's I think I add in this one as an extra question. All right, so it asks you to calculate the heat loss due to the power. Then you have a circular pipe with dynamic viscosity, so and so, and you have a flow rate of this one. Let me check this one. Oh, this one is question 25 in your tutorial. Okay, this is question 25. Question 25 in your tutorial. But anyway, we will just go through very fast because this one is all should be covered. This one for the in previous Friday. Right, I go very fast. Yeah. So this is head loss. So how we apply for the first case when we have 4 liter meter per minute. So again, call out the Reynolds number. So Reynolds number, we know that is given under Moody chart. So is Reynolds number is rho Vd divided by mu. So all the value is we assume we're having a standard condition. So you plug in all the parameter for Reynolds number, right? So in this case, we have a Q. It is 4 liters per minute. Again, in previous example, we already covered how to convert liter into meter cube already, right? Yeah. And in application or when you go to work, most of the time your customer will give you, excuse me, will give you in liter rather than meter cube most of the time. So you need to do conversion when you design a pipe system or pump system. So Q equal to VA, right? Then you do conversion, you get in meter cube per second. You calculate the area because your Q, you need to Q equal to VA, right? Then you get your V. V hat means average velocity, right? You substitute inside there, you get your Reynolds number, 1856. So you get Reynolds number less than 2000, in this case is laminar flow. Okay. Then another one is that this one is for the head loss equation, just application. We have two Poiseuille equation or Darcy equation to find what is needed. Right, this one you can go through. So you can find the delta P by using Poiseuille equation in this case, because it's a laminar flow. And then the head loss, friction head loss equal to delta P divided by rho G. Right. This one also inside the slides. So you substitute all the value, you get one of the 92.4 10 power 3 meter of water. Right. Another one is using the Darcy equation. So this one. And then our friction is 1 over 16 over RE. You substitute all the value, you will get your HF also. Right. 2.4. So both give you the same answer. And then power also given by this equation, P equal to rho G head loss Q. Substitute, you get your pressure, not pressure, power, 0.6 watt, 0.6 watt. So this is the power that you need to select the correct pump or turbine or devices for the system. And for case B, 30 liter per minute. This one, surface roughness given. You just find the Reynolds number again. Again, Q, V to QA. Do the calculation for the V. Substitute in, you get Reynolds number 14 something. Means this one is turbulent. So when it's turbulent, we'll use Darcy equation. All right. Relative roughness K divided by D. And then use a Moody chart. Or for Moody chart, you enter from bottom of the axis. And you get your F, then you find your head loss. So HF 0.4 meter, about 5 meter water. Power required is 24 watt. Okay. So question 24, or this example 25, is application of Darcy equation and combination of Moody chart. Okay. Right, so this one you go through. Okay, this one we will need to go through. Okay, now this question is from question 25. Right? Question 25. Right. Question 25. Again, the rest of the equation, the Chevy, all this, you read from the PowerPoint slide. Because the derivation is quite lengthy, so I don't want to go deep into that. Okay, we go for a short break. Now it's 9 o'clock. We come back. Is half an hour enough for you guys?
Yeah. Yeah.
Okay, so we come back 9:35.